Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 8th, 2025, which was about 1 week ago. The headline result is a practical way to plug high-fidelity image generation into pre-trained multimodal language models while fully preserving their reasoning skills, using patch-level CLIP latents to bridge to a diffusion decoder with far lower training cost. The paper is titled BIFROST-1, Bridging Multimodal LLMs and Diffusion Models with Patch-Level CLIP Latents. And as we will see later, the implications for training efficiency are quite significant. In short, the method matches or beats prior bridges on quality, remains compute efficient, and keeps the language backbone untouched. Building on that, the tweets highlight a unified bridge using patch-level CLIP latents to connect multimodal language models and diffusion models, praising training efficiency and quality. Engagement looks solid, around 200 likes each. Alright, this figure contrasts 3 routes for adding image generation. On the left, a single architecture feeds both text and image tokens into one large model, which is powerful but costly and risky for reasoning. In the middle, a bridge passes one-dimensional tokens between a language model and a diffusion model, which misses detailed spatial structure. On the right, the proposed setup sends 2-dimensional patch-level CLIP latents predicted by a visual generation branch into a latent control net to guide diffusion with precise spatial cues. Okay, let's walk through the diagram. The left block shows a frozen multimodal language model, plus a parallel visual generation branch that shares most parameters, but adds a new vision head. During training, some image patches are replaced by mask tokens, and the branch predicts patch-level CLIP latents. Moving right, those latents are downsampled, reshaped into a 2-dimensional grid, and passed to a latent control net, which conditions a pre-trained diffusion model to render the final image. Now, this table compares bridging designs on ImageNet at 256 by 256, reporting FID and SFID lower is better, and inception score higher is better. Focus on the bottom row. Patch-level CLIP latents with latent control net achieves 25.77 FID, 53.67 SFID, and 98.57 inception score. Building on that, cross-attention conditioning is noticeably worse, and swapping in VAE features or a non-aligned SIG-LIP encoder collapses quality. 2D learnable query tokens also lag far behind. Next, these plots track reconstruction as we scale the number of patch-level CLIP tokens. More tokens, like 256, consistently win. On the left, lower RFID drops fastest and lowest with more tokens. Moving right, SSIM and PSNR rise steadily with token count, showing sharper, more faithful reconstructions. Finally, LPIPS falls the most when using 256 tokens, indicating perceptual similarity improves quickly, even within one training epoch. Moving to the results, this table stacks unified models against several generation benchmarks, listing base multimodal language models, training scale, and 4 metrics. Focus first on the shaded rows, which show BIFROST-1 with Quen 2.5 volts L3B and 7B. Despite only 9 million and 62 million image text pairs, the models post solid MJHQ FID and lead strong on general eval and DPG bench. Compared with heavier baselines like Janus and MetaQuery, the efficiency quality trade-off looks highly favorable. Building on that, 2 takeaways stand out. Using 2-dimensional patch-level CLIP latents gives precise spatial control while keeping the language backbone intact, and the latent control net delivers high image quality with far less training compute. CLIP latents are patch features aligned to the model's vision encoder. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.